Today we're going to explore one of the most fascinating topics in controlled drug delivery and smart materials: how we can trigger the release of contents from microcapsules using acoustic waves, light, or external fields. First, let me explain what microcapsules are. Microcapsules are tiny spherical shells, typically ranging from 1 micrometer to 1 millimeter in diameter, that encapsulate an active substance inside. The shell acts as a protective barrier, while the core contains the payload. This could be a drug, a catalyst, a fragrance, or any active ingredient we want to deliver at a specific time and place. Now you might ask, why do we need triggered release? Why not just let the capsules release their contents naturally? The answer is control. Triggered release gives us precise spatial and temporal control over when and where the payload is delivered. This is crucial for targeted drug delivery, reducing side effects, and maximizing therapeutic efficacy. It also minimizes premature release. We want the capsule to remain stable during storage and transport, only releasing its contents when we actively trigger it at the target site. There are 3 main physical mechanisms we'll discuss today: ultrasound or acoustic triggering, optical or light-based triggering, and external field triggering using magnetic or electric fields. Let's start with ultrasound. Ultrasound uses high-frequency sound waves, typically between 1 and 10 megahertz, to rupture or permeabilize microcapsule shells. When ultrasound waves hit the microcapsules, several physical phenomena occur that can rupture the shell. The primary mechanism is acoustic cavitation. As ultrasound waves propagate through the medium, they create alternating regions of high and low pressure. In the low-pressure regions, microscopic gas bubbles form and grow. When these bubbles collapse in the high-pressure phase, they generate extremely high local temperatures and pressures. We're talking thousands of Kelvin and hundreds of atmospheres in a region just micrometers across. The violent collapse of these cavitation bubbles creates shock waves and microjets that mechanically damage nearby microcapsule shells. Let me show you a back-of-the-envelope calculation. What kind of pressures are we talking about during cavitation bubble collapse? The maximum pressure from a collapsing bubble is approximately equal to the density times the speed of sound times the rate of bubble wall collapse. For water, the density is about 1,000 kilograms per cubic meter, and the speed of sound is about 1,500 meters per second. During violent collapse, the bubble wall can move at speeds around 100 meters per second. So the maximum pressure is approximately 1,000 times 1,500 times 100, which gives us 1.5 times 10 to the 8 pascals. That's about 1,500 atmospheres. This enormous pressure is more than enough to rupture polymer shells. Now let's talk about optical triggering using light. The most common mechanism is photothermal heating. You might wonder, how can light, which is just electromagnetic radiation, mechanically break open a capsule? The key is to incorporate light-absorbing materials into the shell. Common choices include gold nanoparticles, carbon nanotubes, or organic dyes that absorb strongly at specific wavelengths. When you shine laser light at the appropriate wavelength, these nanoparticles absorb the light energy and convert it to heat. This creates intense localized heating at the shell surface. The temperature can rise by tens or even hundreds of degrees Celsius in microseconds. The rapid heating causes thermal expansion of the shell material and the encapsulated contents. This generates enormous mechanical stress that can crack or rupture the shell. For biomedical applications, near-infrared light is particularly useful because it penetrates several centimeters into tissue, allowing triggered release deep inside the body. Let's estimate how much the temperature rises when a gold nanoparticle absorbs laser light. The temperature change equals the laser power times the absorption cross-section times the exposure time, divided by the density times volume times specific heat capacity. Let's say we have a laser power of 1 watt per square centimeter and a gold nanoparticle with an absorption cross-section of 10 to the minus 10 square centimeters. The shell volume near the particle is about 10 to the minus 15 cubic centimeters, with a density of 2 grams per cc. The specific heat is about 1 joule per gram Kelvin, and we expose it for 1 microsecond. Plugging in the numbers, we get a temperature rise of about 50 Kelvin, or 50 degrees Celsius. That's enough to cause significant thermal stress and potentially melt or degrade polymer shells. Besides photothermal effects, light can also trigger release through photochemical mechanisms. Some microcapsules incorporate photocleavable chemical linkers. When these molecules absorb light of the right wavelength, they undergo a chemical reaction that breaks bonds. Breaking these chemical bonds can destabilize the entire shell structure, causing it to disintegrate and release its payload. The advantage of photochemical triggering is extremely precise spatial control. You can focus a laser to a spot just a few micrometers across, releasing cargo from individual capsules. Now let's discuss magnetic field triggering. This approach uses magnetic nanoparticles embedded in or near the capsule shell. When you apply an alternating magnetic field, these nanoparticles experience forces and torques that can mechanically disrupt the shell. One mechanism is magnetic hyperthermia. In an alternating magnetic field, magnetic nanoparticles repeatedly flip their magnetization direction, and this generates heat through hysteresis losses. Another mechanism is direct mechanical actuation. The oscillating magnetic field causes the particles to vibrate or rotate, creating mechanical stress that can crack the shell. Let's calculate how much heating power we can generate with magnetic nanoparticles. The volumetric heating power equals μ0 times pi times the frequency times the magnetic field squared times the imaginary part of the susceptibility. Typical values are a frequency of 100 kHz and a field amplitude of 10 kA per meter. The imaginary susceptibility is around 0.1 and μ0 is 4 pi times 10 to the minus 7. Multiplying these together gives us about 10 to the minus 7 times 3 times 10 to the 5 times 10 to the 8 times 0.1. That's approximately 300 kilowatts per cubic meter. For a microcapsule with embedded nanoparticles, this generates significant local heating. Electric fields can also trigger release, particularly through a mechanism called electroporation. Electroporation occurs when you apply a strong electric field across a membrane or shell. If the field is strong enough, it creates temporary pores in the material. For polymer membranes, the critical field strength is typically around 1 megavolt per meter. Electroporation is often reversible. It permeabilizes the shell temporarily, allowing controlled release without completely destroying the capsule. Now let's compare these different triggering methods. Each has distinct advantages and disadvantages. Ultrasound can penetrate deep into tissue and doesn't require special particles in the shell. However, it has limited spatial resolution, typically around 1 millimeter. Light-based methods offer excellent spatial resolution down to micrometers, but penetration depth is limited, especially in biological tissue. Magnetic triggering provides deep tissue penetration and good biocompatibility, but requires incorporating magnetic nanoparticles and specialized equipment. Electric field triggering gives very fast response times, but is generally limited to surface applications or ex vivo use. The choice of shell material is crucial for triggered release. Different materials respond differently to each triggering mechanism. Polymer shells like polyelectrolyte multilayers can be designed to be mechanically weak or thermally sensitive, making them responsive to multiple triggers. Lipid shells are particularly sensitive to thermal triggers because lipids undergo phase transitions at specific temperatures. Silica or ceramic shells are more mechanically robust and typically require higher energy inputs like ultrasound cavitation to rupture. An important question: what controls how fast the payload is released once we trigger the capsule? If the trigger creates pores rather than complete rupture, the release rate is controlled by diffusion through these pores. Fick's first law tells us the flux equals minus the diffusion coefficient times the concentration gradient. The characteristic release timescales as the capsule radius squared divided by the diffusion coefficient. For a 10 micrometer capsule and a small molecule with diffusion coefficient 10 to the minus 10 meters squared per second, the release time is about 1 second. But if we rupture the capsule completely, release can be nearly instantaneous. This gives us two distinct modes: burst release when the capsule ruptures, or sustained release when we create controlled permeability. These triggered release mechanisms have revolutionary applications in medicine. In cancer treatment, we can inject microcapsules loaded with chemotherapy drugs. By focusing ultrasound or light on the tumor, we trigger release only at that location, minimizing side effects on healthy tissue. For chronic conditions, we can implant capsules that release medication only when triggered externally, giving patients control over their treatment. Some capsules combine imaging agents with drugs. We can use ultrasound or MRI to visualize where the capsules accumulate, then trigger release precisely at those locations. Beyond medicine, triggered release has exciting applications in smart materials. In self-healing polymers, microcapsules contain healing agents. When the material cracks, we can trigger release to repair the damage. In responsive coatings, capsules release corrosion inhibitors, antibacterial agents, or fragrances on demand. In chemical processing, we can trigger the release of catalysts at specific times and locations to control reaction pathways. Despite the tremendous promise, there are still significant challenges to overcome. For medical applications, we need to ensure that shell materials and any nanoparticles are biocompatible and can be safely cleared from the body. Many sophisticated microcapsule designs are difficult to manufacture at scale with consistent quality. Achieving both deep tissue penetration and precise spatial control remains a fundamental challenge. There's an inherent trade-off between these properties. Let me summarize the key physics principles we've covered. All triggering mechanisms ultimately work by generating mechanical stress in the shell, whether through cavitation bubbles, thermal expansion, or magnetic forces. We convert electromagnetic energy, sound waves, light, or fields, into thermal or mechanical energy at the microscale. The shell material responds by fracturing, melting, or becoming temporarily permeable, depending on the trigger intensity and material properties. We control release by tuning parameters like frequency, intensity, and duration of the applied stimulus. Triggered release from microcapsules represents a beautiful intersection of physics, chemistry, materials, science, and engineering. As we develop more sophisticated materials and better understanding of the fundamental mechanisms, we're moving toward truly smart drug delivery systems that can target diseases with unprecedented precision. The ability to control release with sub-millimeter spatial resolution and sub-second temporal resolution opens possibilities we're only beginning to explore.